Welcome to the 12th talk in the inaugural webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, their families, and their colleagues are safe amid the ongoing COVID-19 pandemic. Today's webinar will be presented by Professor Arvind Rajendran of the University of Alberta. I'm Daniel Siderius of NIST in the United States and the Secretary-Treasurer of the IAS. Questions to our speaker will be moderated by Valentina Stampi-Bembelli of ETH Zurich and Nicholas Wilkins of the University of Alberta. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or of the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only $20 per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter for future updates regarding IAS events, webinars, and information about scientific meetings. Please help expand our YouTube channel by subscribing. We also ask that you would help us evaluate this webinar series by taking the online survey at the bit.ly URL shown on screen. This link is also available on IAS Twitter. We will use the survey results in planning for future webinar series and other IAS events online. During the webinar, questions can be submitted to the speaker via the Q&A tab of the Zoom client or as comments on YouTube, and those comments will be forwarded to the Zoom hosts. Questions will be addressed midway through the webinar and again following the end of the presentation. I am now pleased to introduce today's speaker. Professor Arvind Rajendran is a professor of chemical engineering at the University of Alberta. Additionally, he is a director of the IAS, an area editor of our Society's journal, and an associate editor of the Canadian Journal of Chemical Engineering. His research and teaching interests are in adsorption process engineering and process optimization, as well as in the application of modeling and machine learning to adsorption processes. Today, he will present on lessons learned from large-scale screening of adsorbents for CO2 capture.
Excellent. Okay, so thank you so much, Dan, for all your technical support and also helping in arranging this wonderful meeting. I should also thank Andreas Seidel-Morgenstern, the president of the International Adsorption Society, for his support in getting this webinar going. So I also want to check that all viewers and listeners are safe and they're doing well. When we started organizing these webinars, one of the key objectives was that we could reach out to the audience that we traditionally don't. Very often, we as chemical engineers address our colleagues in chemical engineering, but I think there are many problems that we have to tackle that lie at the interface of chemistry, engineering, systems, and policy. And that is what I'm hoping that we could achieve today. And there's also a wonderful opportunity because I also have my family watching from the next room and possibly my mom watching from India. And I think this is this medium provides this very unique opportunities. So before I start, I should thank all our grad students who are shown here. They are the ones who do all the wonderful work, and also to thank all our funding partners as well. So when I wanted to give a talk on this webinar, so I was wondering what is the most appropriate aspect, and I landed upon this title as to what are the lessons that we learned from large-scale screening of adsorbents, and particularly on CO2 capture, because that is an area where we have done quite some work. And as a tribute to my former PhD advisor, I could have also called this talk as Dr. Sarp's Screen, or how I learned to stop worrying about metrics and love the model. He's a big Stanley Kubrick fan, so this is for him. So the target audience and the agenda that I would like to address today are as follows. So my target audience for today is mainly researchers that work on materials development, both experimental and modeling, and who are keen to understand how adsorption processes work. At the end of the webinar, my aim is to give you an idea of how cyclic adsorption processes work, and also describe how sorbent screening is currently done in many groups, and how it could be done in a better manner. So I've kind of divided my talk into part 1 and part 2. The whole point of this talk would be to also convince you that there is a dialogue that is needed between chemists and engineers, because the problems lie at really that interface. So the scope for my talk would be as follows. I would only focus on what are called as equilibrium separations using the technology called as vacuum swing adsorption. There are many other techniques, and I will not talk about those. And I will particularly focus on CO2 capture for today. I should also give you a disclaimer. In order to convey some very key messages, I would have to simplify, or in some events even oversimplify some of the concepts. So I hope my colleagues would forgive me for that. But I would also direct you to read the relevant literature for clarity. So this slide I really made for my family, so I hope you will indulge me in that. So what are we talking about here? In an adsorption process, we start with a material, a solid typically, which is called as an adsorbent. And these tend to be porous solids, which means that they have very tiny pores inside them. And they could have, as we heard from Stefan Kaskel yesterday, thousands of square meters per gram. So that's a lot of real estate, but you see that real estate only if you're a gas. So what we do there is we take these solids and we pack them in a bed. And for example, if our objective is to separate a mixture of gases, for instance, let's say A and B, we can utilize the potential of this material. Some materials have this potential that, for instance, here, A, which is often called as the heavy component. In this presentation, it is CO2. And we have a light component, which is nitrogen, B. So note that the heavy and the light are terminologies that are borrowed from distillation. But in this context, what it means is that A sticks more to the adsorbent, or in other words, A is strongly adsorbed on the adsorbent compared to B. So if I pack this column with such a material, and if I now feed in a mixture, which contains both A and B, and here on the right-hand side, I'm showing you an animation. The first plot here on the left shows how the fronts of A and B will propagate through the column. And the second plot I show here is what will be the composition if you measure at the exit of the column. Okay, so let me get this started. So as you can see here, since A sticks strongly to the adsorbent, it moves much slower as compared to B, which is moved ahead, and it is already showing up at the end of the column. So what you see now is component B coming out, and you see that we are purifying or enriching that component, because you can see that what went in as a 50-50 mixture is now 100% pure B. And this happens until the second component, which is component A, starts to break through, as we would call it. And then beyond a certain time, the bed is now fully saturated with your feed and you don't see any separation anymore. So what it means is that really for a period of time, in this case, you can collect component B in a pure form. Beyond that, the bed is saturated. And if I have to now reuse the bed, I have to regenerate it. So which means that I would have to clean it in some way. And then we will have to use it again and again. So although I show that only component B comes out in a pure form, when you do the reverse, which is to regenerate, there is a potential to get component A in a pure form. So this is the basic principle upon which adsorption separation processes work. And they're all about how these fronts move through the column. And if you want to know where this is applied in many cases, and I'll just show you two examples here just to show the scale of this operation. Oxygen PSAs, which have now, or VSAs in some case, have now come to the forefront also because they are portable and they work on just on a battery device, and you could have a small device which looks like this. All that has inside is a pump, possibly some valves, and the adsorbent that is packed. What it does is that it can take the oxygen in air, which is about 21 mole%, and it can enrich it up to about 93%. You can have very small devices, which are for personal use. And in the industrial scale, you could go up to about 400,000 normal meter cube per hour in the case of hydrogen separation. So this also shows the versatility of adsorption separation processes, which can go from very small scale to very large scale. There are also other applications, of course, which you can read from the literature. So if you're interested in understanding, either as an undergraduate or as a graduate, so here is the list of books that I would recommend. So I've kind of classified them as books that are probably suited for undergraduates, and then more detailed books for researchers. So let us come to the problem that we are trying to address today, and this is called as post-combustion CO2 capture. So I've kind of represented this in a simple schematic. You might have heard Marco Mazzotti talk about this in a more a grander scheme in his talk. So what we have here is a coal-based power plant. It could be natural gas, for instance. All that would change is the compositions and the flows. But to simplify this, what we're doing is we're taking a fossil fuel, in this case, a coal, and we are combusting it in air. And of course, the objective of doing this is to generate power. So for instance, the 550 megawatts is a kind of a standard power plant notation that people in the community use. So if you have to produce 550 megawatts of power, you also produce flue gas. And the flue gas can be in very huge quantities. For instance, a power plant of this size could produce all the way up to 55,000 tons per day of flue gas. And in order to simplify the process, we are going to assume that it contains predominantly nitrogen and CO2, because nitrogen comes from the air and CO2 is the product of the combustion. Of course, in this case, you will also have water, and very often this flue gas is also fully saturated with water. This is usually available at or around ambient pressure and temperature. The composition of CO2, which is a very critical point, can be anywhere between 12 to 15% if it is coal, and up to about 8% if it is natural gas. Okay? So the whole idea is this contributes to CO2 emissions, and the objective is to build a CO2 capture plant where you can separate CO2 from nitrogen, and you want to concentrate CO2. Typically, the targets are in excess of 95% in order for it to be either sequestered or for use downstream. And then you also have the bulk product, which is nitrogen, because about 80–85% of your flue gas is about nitrogen. So the nitrogen and unrecovered CO2 leaves this unit. Of course, it would be nice if we could do this for free, but thermodynamics does not allow us to do that. So what we need to do is we need to take up energy, and very often this is taken from the power that is produced by the power plant, and this is what is often referred to as the parasitic energy. So if you look at this schematic, what we want to do is we want to purify CO2 up to about 95%. And we want to do it by minimizing the energy that is removed from the power plant, and also to build a plant that is as small as possible. So what are the challenges that we see? The key challenges are the following. So one is we are dealing with the low CO2 concentration. For example, people that are trying to capture CO2 from the air have a far bigger challenge, because CO2 concentration in the air is only about 400 ppm, whereas here we are dealing with a much higher concentration. But even considering that you have about 15% CO2, that is often considered as a reasonably diluted stream, because you want to take that CO2 from about 15% to 95%. So the concentration is one big challenge. The second is, of course, you're dealing with huge volumes. This is of the scale that many plants have not encountered in practice. So this is a real challenge that engineers have to deal with. There are also constraints, and the constraints are really that you have to have very high purity, in excess of 95%, and regulatory bodies such as the US Department of Energy, in some cases where they would like you to decarbonize much more, require that you also capture 90% of the CO2 that enters here as your product. So this is often called as the recovery. So when you're designing these plants, these become very critical. And of course, the objective is to do this and achieve your product requirements by minimizing the parasitic energy and also maximizing productivity. The productivity is a term that we use to denote how much you can capture using a given amount of material. in a unit time, for instance. In another way, it talks about the size of the plant. So when you're thinking about this from an engineering perspective, these become very, very critical in order to design a suitable process. And this is something that is often overlooked when people are developing new materials for CO2 capture. And of course, in this talk, we are interested in looking at using adsorption as a method to do this. And again, let me emphasize that I'm not really going to talk about why CO2 capture is important, but treat this as a separation problem that we have to deal with. So before we do that, one of the key ideas that I wanted to talk about today, and also in the spirit of the webinar series, is also to give an introduction to adsorption processes. And I will talk to you about the pressure and vacuum swing processes. And this is really to aid our colleagues in materials development to understand what are the nuances in adsorption process design. So as I told you earlier, adsorption processes alternate between adsorption and regeneration steps. This is because in the animation that I showed you, you saw that the fronts kept moving, and at some point, both components fully occupied the column, and at that point, you had to clean the bed, essentially. The adsorption processes, in terms of how they are classified, really depend on the method by which we regenerate the bed. For instance, I show here what is called as an isotherm. An isotherm is nothing but, for a given pressure, how much of a gas is adsorbed on the solid, and that is called as Q star. So as I've told you earlier, we have two components, A shown here in red and B that is shown in blue. As you can see here, at any given pressure, A is strongly adsorbed, which means its loading is much higher than that of B. So when you now take, for example, the isotherm of A, in order to illustrate this, you might have been working at a high pressure, at a higher concentration, so your bed would have been saturated up to this point, and now you have to regenerate the bed, which means you now have to somehow decrease the concentration of the gas in the solid phase. And classically, in the case of gas systems, this is done either by reducing the pressure, so you start from this point here, and you reduce the pressure, you reach a pressure which is PL, which is a low pressure. And as you can see here, you have removed an amount that is given by this, the difference between the higher loading and the lower loading, which is given here by this green difference. And this is often referred to as the working capacity of the adsorbent. You can also now change the temperature, because adsorption is an exothermic process. So which means if I now work at a higher temperature, the loading is lower. So you can exploit that difference, and you can increase the temperature by going from a lower temperature to a higher temperature, that is T1 to T2. And that also results in releasing the gas that was adsorbed. And again, here in this case, this difference is called as the working capacity. By no means, I would like you to take home a message that PSA gives a higher working capacity as compared to a TSA, but this is really for the purpose of illustration. So when you now swing the pressure, it is called as a pressure swing adsorption. And when you swing the temperature, it is called as a temperature swing adsorption. There are also other ways in which you can regenerate the solid. And one of the ways is called concentration swing adsorption. It's rarely a terminology that is used in practice, but it is a concept that is heavily used, for example, in liquid chromatography, where you use a solvent in order to desorb. And often these days, we are also seeing some examples where you could use steam, a condensable vapor, as a way to decrease the concentration, and very often in gas adsorption that gets classified as a TSA process, but in reality it is a concentration swing process. There are also other ways like microwave and electrical heating. We have seen some examples of that, but they are, in my view, they are in a much earlier stage of development. So now, the one point that we have to realize is that for the sake of simplicity, it would be reasonable to say that an adsorption process is often decided not by the adsorption step, but really by the desorption or the regeneration step. Now, when you have so many choices, how will you now pick one of these methods for your problem. So there is really, there are some broad guidelines. For example, very often if you have to purify your heavy component, people recommend temperature swing adsorption. But very often these days, pressure swing adsorption is also being increasingly used for purifying the heavy component. So the point being that the choice between any of these processes really depends on the separation problem that you're dealing with. But one of the key aspects is, if you look at this diagram, this is often used as an illustrative diagram to understand what happens in this case. But one of the cautions that I would give you is that it is good in order to understand qualitative differences, but I would urge you not to use these plots for making major decisions. To put the complex argument in a much simpler words, very often these diagrams tend to show that pressure swing adsorption happens at a constant temperature, and a temperature swing adsorption happens at a constant partial pressure, and neither of them is true for a real process. So what it means is that making judgments of how a process is going to perform simply based on these isotherms is not suggested. It is good to understand the qualitative reasons, but not to make hard decisions. So what are the unique features of adsorption processes? Very often in adsorption processes, we talk about two products. One is called as a raffinate product, enriched in the light component, in this case, nitrogen, and the extract product, which is enriched in the heavy component, which in this case is CO2. A few characteristics distinguish adsorption processes from processes such as distillation, which chemical engineers know for a much longer time as compared to adsorption processes. Some of the key ones are the following. One is we don't reach what is called as a steady state operation in adsorption process. And this is really a message for undergraduate chemical engineers, because most of what we teach in undergraduate chemical engineering deals with steady state operations, because it is easier to write design equations under those conditions. What it also means is that these processes reach what is called as a cyclic steady state, and I'll show you an illustration in a moment, and they don't reach a true steady state. And as I will show you later, unlike traditional processes, because these are built on modular schemes, there are many different ways in which you can combine these small modules, as I will show you in the next slides. And this leads to a wide variety of possible processes that you can develop by just combining elementary steps. All that it means is that we don't have any straightforward design tools for these. And this makes the problem far more challenging as compared to designing other separation processes. I should also note that adsorption processes that are commercialized are typically for raffinate products. For example, the oxygen production that I showed you earlier, a zeolite typically adsorbs nitrogen more strongly compared to oxygen, and that's also the same for the hydrogen production. But there are recent works and some commercial operations where the extract purification, which is the concentration of the heavy product, is also being practiced. In CO2 capture is an example of an extract purification. And I would also say that in most processes, both products are not obtained in the pure form. You are usually targeting for either one of these. There are exceptions to this, but very often you're either targeting for a pure raffinate or a pure extract product. So when you talk to an engineer who is designing adsorption processes, we talk about performance indicators. And we usually talk about 4 performance indicators. I have listed the performance indicators on the left-hand side column. And from a process perspective, these indicators can either be given to you as a specification that you have to meet, or it could be an outcome. It could simply be the result of how you design your process. And I've also put down some notes in the last column here. So the first one is, of course, the purity. How pure is my product? Very often this is a specification. So you have to meet this because your downstream production or your user requires this at that level. So this is almost a hard constraint that you cannot violate. The second is recovery. So in the recovery, all that you're saying is if I put in 1 kilogram of my component in the feed, how many kilograms do I get back in my product? You can either talk in kilograms or in moles, but it essentially tells you how much of what you put into the process is recovered as the product. In some cases, this is a specification. For example, as I mentioned before, the US DOE calls it as a specification for recovery. In many other cases, it is simply an outcome because you're not really targeting recovery. You might be targeting energy, for example. What is the impact of having low recovery? Low recovery, especially if you're talking about a valuable product, means that you might have to recycle, and recycling costs both size and energy. So in a process, you're always trying to squeeze in every bit of recovery that you can from the process. So the other two are often energy consumption. And in a vacuum or a pressure swing, it could either be evacuation or compression energy that you put in, or in the case of a temperature swing adsorption, it could be a heat. Note that this is often the clearest indicator of the operating cost. And for small units, energy consumption becomes the most important characteristic that you are targeting. Of course, the next one is productivity. And as you see here, I've defined productivity as the moles of the target species in the product divided by the cycle time. So in a per unit time per mass of adsorbent. The productivity is an indication of the size of the unit. So you often want to maximize the productivity. And hence, it is also an indication of the capital cost. It could be the determining factor for large scale units, and CO2 capture is one such case. So whenever we are trying to measure, for example, how well an adsorbent performs, we have to keep in mind that it satisfies all of these specifications and it achieves the desired outcome. So that is how we should be moving forward with the assessing adsorbents. So this is the only equation slide that has any kind of mathematical equations. But I would just like to put it in here to convey the message that what you have in these processes are, they are dynamic systems. So you have properties that are changing in time, and they're also translated. The fronts of heat and mass get translated in space. So you're also looking at propagation in space. So you have both the fluid phase mass balance, you have an overall mass balance, and we of course have to track the temperatures as well. And this is given by the energy balances. We have to characterize the pressure drop in the system. And for the specialist, the mass transfer, which is the rate at which the gas goes from the fluid phase to the solid phase, is also something that is very critical. It has a huge impact on the size of the unit, and that has to be characterized well. Finally, the more important factor in this case is the isotherm, which determines how the loading of a particular component on the solid phase is related to its concentration in the fluid phase. And note that very often, and almost always in bulk separations, as we call it, you have this denominator which indicates the competition between different species. And this plays a huge role in deciding how a material or a process could perform. So if you look at the pressure or vacuum swing adsorption processes, they are constituted of various steps, and I've put in a few building blocks. The first one is called as pressurization. So the idea here is that you close one end of the column and you introduce the gas from the other end. And what this does is, since this end is closed, it increases the pressure. So in terms of the fronts that I showed you in the animation, what it does is imagine that you're closing this and you're pushing something. So it ends up sharpening fronts in a very qualitative manner. The next step is, of course, feed, because you want to separate, and this is the key step. And what you do is you open both ends and you introduce the feed from one end. This is the mixture. And on the other end, as I showed you in the animation, you get a purified light product. What this does is, since both ends are open, the easiest way to imagine how fronts will propagate is that the fronts get translated in space as this step proceeds. The third building block is called a blowdown. What you do is you do the reverse of a pressurization. You close one end and you decrease the pressure by opening the other end. And note that this means that at this end, at the top end here, the velocity is 0 and the velocity is huge at this end. So what happens is that the fronts get stretched in this direction. And in these processes, they are used to remove the product in some cases, or you also use it to remove the undesired species. we use a very interesting step which is called as pressure equalization. And this is really if the column on the right is at a low pressure and the column on the left is at a high pressure, you can take the material from the column on the left and use that to pressurize the column on the right. This is a step that helps us to conserve energy. And what it does is it spreads the front on the left column, and it sharpens the front on the right column. Chemical engineers who are familiar with the refluxes would probably remember this. This is called a purge. And what we do is we take part of the product that comes from one column and we use it to flush the other column. And this is called as a purge. And this acts just like your feed step. So this means that this again translates your front. So think of all of these as Lego blocks that you can put together to start building new and complex processes. Let's build one process. I've shown you here a process that has 4 steps. This is called a 4-step process. What we do here, we start with a CO2 and nitrogen being introduced as a feed, and you get nitrogen as the raffinate product on the other end. And now the column is fairly filled with CO2 and nitrogen, and since nitrogen is adsorbing to a lesser extent, we remove that by lowering the pressure. So we go from a pressure high to an intermediate pressure. And the objective here is to remove as much nitrogen as you can, but without losing CO2. There is no way that you can choose only to take out nitrogen. CO2 will obviously leave depending on the equilibrium. And the last step is to remove the product. And you can imagine that since you fed CO2 from this end, CO2 would have been concentrated at the bottom of the column. So you pull another vacuum. In this case, you go down to PL and you remove your product, which is your CO2. So this is really where you get the product. And now the column is at a low pressure. You need to take it back to a high pressure and you introduce the feed to do this. In the most simplest of cases, I have identified the operating parameters. For example, you could have chosen a different length of the column. You can choose how fast or how slow you're going to introduce the feed. And in many cases, you can also decide what should be the duration of the steps for which each of these steps are going to be carried out. And of course, you can choose what could be the intermediate pressure and the low pressure. I've fixed the high pressure in this case simply because in our case, the feed contains a lot of nitrogen, and people have found that it is not advisable to pressurize a feed that has 80–85% nitrogen. So what I'm going to show here on the right is to show how the fronts are propagating. And what we're going to do is we are going to start from one of these steps, move from here to the next step, to the next step. And then we are going to keep repeating this until what we would see as a cyclic steady state. So initially, the column is saturated with nitrogen and we are introducing a feed. So what you see here on the left-hand column are axial profiles going from 0 to the length of the column. We show the CO2 gas phase, the temperature in the column, and then you also have the solid phase loading, which is given by the CO2, and the nitrogen, which is in the dotted lines. And on the right-hand side, these are performance metrics. For example, this gives you how the CO2 purity in this product evolves as a function of time. And I've also shown you how, if you measure, for example, the temperature somewhere in the column, how that temperature would vary. And the bottom plot here, bottom right, is showing you how the pressure in the column varies. So let me run this simulation, and thanks to Gokul for this wonderful animation. As you see here, these fronts start at around 0.2, and this is in cycle number 4 and 5. And you see, as the cycle increases, you slowly see that this front starts to move through the column. So this is where the unique feature of cyclic adsorption processes come in. As you can see here, initially, the purity that you obtained was about 50%. And as the cycle proceeds, it goes all the way up to 80%. And it reaches a constant point at, in this case, about 100 cycles. In some other processes, it could be much longer. What you also see is a temperature wave that is propagating. As you see here, this is measured at around 20% in the column. You see that the temperature increases and then it decreases and then it becomes stable. But if you notice very carefully, within a cycle, the temperature, of course, keeps fluctuating. This is also illustrated on the left-hand side. As you can see, the temperature in the bed can vary along the axial direction, depending on the cycle, depending on the system that you're dealing with, up to about 20–30 degrees in this case. It could be much larger in some cases. So this is how a PSA or a vacuum swing adsorption works. So when you run this to the end, you can also now look at how the CO2 solid phase loadings are. And as you can see here, for this particular set of operating conditions that we chose, it ends up that you're using only about 20% of the bed. Because between the adsorption and the evacuation steps, you see that beyond about 20%, nothing really changes. So it's almost as if this part of the bed has not seen any change in the CO2 loading. And that is because you also want to achieve very high recoveries. So you're trying to balance this obtaining purities and recovery. So this is a trade-off that we always have to keep balancing. Okay. So now the question is, with so many operating parameters, how do I pick the right set of operating parameters? And that is a very, very key question, because very quickly the number of operating conditions can vary, and the choice of your operating conditions really depends on a lot of factors, such as the material that you're using, the adsorbent material that you're using, the feed that you're considering, the pressure levels that you're operating with, and all of this have a choice as to what set of operating conditions are going to give you the best performance for this material and for this process. And for this, we use what is called as an optimization. So what we have is, we have the full model, the set of equations that I showed you earlier, which are solved cyclically, and we have an optimizer. The job of the optimizer, in very simple terms, is it picks, let's say in this case, a whole bunch of operating conditions, and it throws it to the model. So for each operating condition, we call these as decision variables. For each set of operating conditions, the model evaluates the PSA, just like what I showed you earlier, and it returns the performance indicators that we discussed earlier. So what are they? Purities, recoveries, energy, and productivity. And for example, if you now want to have some kind of a constraint, you want to meet, for example, some purities, what you can do is you can look at these performance indicators, see if they meet or not, and introduce penalties. If it does not meet your requirements because it has not met the constraints, you can penalize these, and then you send the objective function back to the optimizer. So, and what we do is we do this repeatedly over thousands of operating conditions. We explore thousands of operating conditions. And when you explore it, you start getting a picture like this. So for example, here I'm showing purity on the x-axis and recovery on the y-axis. And you start seeing these points, and each of these points represents a unique set of operating condition. And the purity recovery values are the values that you get by running the unit at that particular operating condition. So as you can see here, this is what we call as the first generation. It has picked about 60 points, and it has picked them randomly, and that is why you see this very wide spread. And what we do with this optimizer is that we keep running this over many generations. As you see here, the generations keep going up. And as you can see here, now the optimizer is exploring the entire operating space that is available to this particular process. And what you see here is that you slowly start seeing what is called as a Pareto curve. So the Pareto curve is a terminology that we use for a trade-off curve, because the purity and recovery are objectives that work in opposite directions. So you are trying to find what is the best trade-off that you can achieve for this particular material, for this particular process, given a certain range of operating conditions. And what you get here is a region, which is the infeasible region. So beyond this outer surface here is a region that is not feasible. So for example, if you want to achieve a 90% purity and 90% recovery in this case, this is infeasible with this material and with this process. If you choose to operate your process anywhere below this curve, you are operating it suboptimal. You're not utilizing your system to its ability. So where should you operate? You should try to operate as much as possible on the Pareto curve. Now, given the Pareto curve, you as a user will pick what is important to you. So what it means is that if I now need a purity of 90%, the best recovery that I can achieve is only about 85%. Right? So you want to now choose what is it that you're willing to let go and what is it that you're not. So this gives you a very objective way now to analyze what is the best possible scenario for this particular process. So for example, here I've shown how the Pareto will change when you now change the low pressure. And as you can see here, as you now start going to deeper and deeper vacuum, of course, you start getting better and better performances. So one point that I would like to note here is that each curve here is obtained after solving about 3,000 odd operating conditions. And this means that you require a lot of computation, because for each operating condition, you have to run this model until cyclic steady state. And then you have to evaluate the performance indicator, and you have to keep doing this again and again. So typically this requires anywhere between 100 to 250, 300 core hours. So which means that if I have a computer with one core, you require up to about 200 hours to do it. If you have access to workstations that have multiple cores, you could do this faster, but nevertheless, this is considerably a large duration of time. Now, the other point that I would like to point out is if I now change one step, so for example, we were pressurizing the system earlier, in this case with the feed. What if I just take the product here and then pressurize the system? This is called as a light product pressurization. And note that this very small change in the process leads to completely different profiles. So if you look at the dashed lines, that is what you got with this process here. And when you now look at the light product pressurization, you have completely changed the profiles in the system, not only the profiles in the system, but also the performance of the system. Note that earlier with the fourth step, you were getting 80% purity with 86% recovery for exactly this operating condition. And by just changing one step, you see that the purity has now dropped to 60%, but the recovery has increased. So this emphasizes how you can change the cycle and get completely different performances. And now this is critical, because if you now think of an adsorbent from the perspective of an adsorbent, or from the perspective of the PSA, TSA qualitative diagrams that I showed you earlier that were illustrated with the isotherm, these both these cases will have exactly the same scenarios. So you will never be able to distinguish the effect of a cycle based on those diagrams. And that is precisely the reason why I said that you have to be very cautious in using those kind of diagrams for making any hard decisions. Now, then your obvious question is, okay, now you have the cycle, can you go any further? Yes, you can. The complexity can just keep increasing. So here, for example, I show you 5 different cycles that can be built with the building blocks that I mentioned earlier, starting from a very simple step and by slowly increasing complexity. Now the question is, I have one adsorbent, I have a limited access to vacuum pumps, for example, which means that there is a limit to which, a pressure limit to which I can go. Which of these is going to do the best for my material, or which of these is going to do the best for the separation problem that we are considering? And this is a point at which optimization comes to help. So now I showed you the purity recovery Paretos after running each process for thousands of cycles. The Pareto curves for each of these processes. There are more shown here, but I would like to draw your attention to, for example, the 4th step gives you a Pareto which is just here. The 4th step with a light product pressurization is green, so it is significantly improved in terms of the trade-off. And if you now go to the pink one here, it shows you that you can do even better. But the point that I would also like to highlight is that here I've shown something in a beige color, and that is shown here. It's almost right behind the brown curve here. And the point is really that just because you're increasing complexity does not mean that this cycle has to perform better than a much simpler cycle. So this is the real advantage of using optimization. So now all of these have the same material, in this case, Zeolite 13X. They are all operating within the same bounds, but just by changing the way in which you build the process, you can get completely different performances. So for example, this is the target that we want to reach. And this clearly helps you to eliminate processes that won't allow you to reach the target, and select those processes that will reach the target in order for you to study further. So this is one of the key messages in the talk, which is the process matters. It's not just the material, the process matters. And I would also add a small addendum. You also have to optimize the process in order to compare how good or bad they are. So here is the proposed development framework, how we propose that we would want to develop adsorption processes. You start by measuring properties, isotherms, and kinetics. And then we send them to a process simulator, which are coupled with multi-objective optimizers. And based on this, you can now scale up your performance and build your experiments. Here is an example. So this is on zeolite 13X, again, CO2 nitrogen separation. So here is what we measured using 300 milligrams in a volumetric device. So, and then we scale it up to a breakthrough. So here you get better information about the kinetics. And then we build processes based on the framework that I just described to you. And once we have the Pareto curves, we could now go to a lab and we can look at the Pareto curves that were obtained theoretically using the models, and we can run experiments. So the dots that are shown here are from experiments that were guided by the model. So the point being that if you have good data, and if you have a good way to simulate your processes, these modeling can in fact help you to drive experiments, and you can also achieve the optimal performance by doing this. What is the advantage of doing this? You save so much of experimental effort, because otherwise, if you do not know where these Paretos are, you might have started here and you might be trying to reach these Paretos. So these approaches save significant experimental effort. So you can ask, okay, how good are these models? We have been working with a company here called Oxygen Solutions, and they make oxygen concentrators, very large scale oxygen concentrators. And they were also gracious to allow us to have access to some of the data. So here, what I show here is the data that is obtained from an instrument that contains 750 kilograms of adsorbent. And back in our labs, we performed isotherm measurements. We knew the pump characteristics and the cycle, and using the process simulator, we predict the performance, and this is using 350 milligrams. So this represents 2 million times scale up. And as you can see here, I'm showing you the difference between what the model predicts and what the plant gave, except for the recovery where we were off by about 10%. You can see that the purity computations, the energy computations, and the productivity computations were almost spot on. And this is impressive because all of these decisions are made from experiments that are done on a 350 milligram sample. In this case, it's an air separation process. So we had some idea of how the competitive behavior is. So, and hence we did not run breakthroughs. So we just went from a gravimetric or volumetric measurements to the scaled up performance. So the message is the scale up is good, provided you have all the inputs. So one of the things that I started doing was to summarize these as tweets. So here is the tweet. I will let you read it, but I will also take questions at this point.
Hi, Arvind. Thank you so much for this first part of your presentation. I will see now if there are any questions from...
Did the YouTube work?
YouTube? Yes, it worked.
Okay.
So it started working as soon as Dan fixed it. So we already have a question in the chat, on the Zoom chat from Guoping Hu. So first of all, he thanks you for your nice presentation, and he asks, so regarding the productivity, you introduced, and most people are reporting, a process gas quantity per unit time per weight of adsorbents. I realize the packing density of adsorbents actually varies significantly depending on the materials. Hence, it may be more meaningful to use process gas quantity per unit time per volume in determining plant size for real industry. Can you please comment on this?
Absolutely. No, I'm fully with Guoping on that. And this becomes very critical, especially when you're dealing with new materials where you're trying to structure these materials into, for example, into beads. And sometimes if you don't find the right kind of a binder, you might end up with having materials that have very low density. What this means is that on a per gram basis, you will get the same loadings, but on a per volume basis, you will get very different loadings, which means your vessel sizes tend to be much larger. So when we start going to the next step, which is to do costing analysis, we of course have to take that into account, and that shows up in the plant size. Yeah, I agree with Guoping.
Great, thank you. And our first question from YouTube is from Angel Hojadi, asking, in some cases, we find fluctuating capacities during consecutive cycles via TSA using TJ analysis. How could we explain this behavior in lab scale?
So I think here, Angel is perhaps talking about what happens in experimental campaigns where they are trying to understand whether the material can be cycled. Very often, it could be moisture or impurities, or it could also be that the material is degrading either because of the cycling or because of the heating. This is a critical factor when you now have to scale this up. And industrially, you see that many of these, I would say, classical materials, they hold good for years. So yeah, so that is how I would answer that.
Great, thank you. Our second question is from Malgorzata Kowalczyk. I'm sorry if I pronounced this incorrectly. Asking, does the accuracy of the optimization depend on the complexity of the separation process?
I would say that the accuracy of the optimization depends on many things. One is to what extent we are modeling the different phenomena. For example, when you start having columns that become much wider, you start having what are called as two-dimensional effects. So now your model has to account for those aspects. The second key input, and I will show this later in my presentation, is also the quality of your input. So your isotherms, your competitive isotherms, how well you know the diffusion characteristics, all of these affect the model. So as a modeler, your model is only as good as your inputs are. So yes, if they vary, of course, your model results would vary. And that is why I believe some level of experimentation is always important to close the uncertainties that you could have with the models.
Thank you. And I think a good follow-up question is by Omid Nick, in which he asks how good our model predictions can be without having binary interaction data.
In some cases, it is easy, and I would say it is very system dependent. And I will show you an example of CO2 nitrogen on 13X, possibly the system that has been beaten to death for CO2 capture. And if you read papers in this area, one is it has been difficult to even get binary data. And second, to describe the binary interactions has been fairly challenging. And later on, I will show you results from both our group and also Stefano Brandani's group, where we have shown that how you characterize them are quite critical. So again, to answer Omid's question, if you are planning to take your material anywhere beyond a few milligrams and into a gram or kilogram scale, you have to have binary data.
Thanks, Arvind. We have a comment and a question from Amir Far.
Yep.
So his comment is that nitrogen isotherms are critical for process-based high throughput screenings. However, there is often no good force fields for them in molecular simulation, and experimental data is also very difficult to obtain. So his question is, what do you suggest the best practice is in this case?
Well, I know Amir himself is a molecular simulations person. So one is, I think we need to get better force fields for predictive capabilities. And secondly, I think doing measurements is the final and the most important step. There is always also a compromise, because when you're now running these simulations, it takes a lot of time. So you also want to make sure that these are what we call as explicit forms, so that you're not spending a lot of time trying to calculate these. Because, for example, if you use techniques such as the ideal adsorption solution theory, which works in some cases and which doesn't work, you spend a lot of computational time just trying to get your binary loading. So there is always this compromise, and I would say you have to be smart and try to find a nice way to characterize them. So if you don't characterize them well, then your predictions may not be very good. And Amir brings up a very important point, and because that really leads to the question of, when we're doing these large scale screenings, what is the reliability of our mixture models, right? So it's a very, very critical question. And that's why it becomes also difficult to take those results from the screening and be any certain about how valuable or how valid they are.
Great, thanks. We're going to have one more question before you start your second part, and the next questions will be for the end of your presentation. So we have a question from Ying Chiang asking if we can calculate purity and recovery from single gas adsorption isotherms, and if it's possible that we can do that from breakthrough curves. Okay,
thanks, Ying Chiang. It's a very important question, and it's a point that I would like to address, and I will address later on. The moment you're talking about a purity, you're talking about two gases. There is no purity in just one gas. So it is almost impossible, I would say it is impossible, to get any purity information if you're just dealing with one gas. The best is you might assume that the other gas does not adsorb. That might give you some indication, but it does not allow you to calculate purity and recovery. So, and the point being, if you're a material scientist, always measure at least CO2 and nitrogen isotherms. Without them, you cannot make any predictions about how the system works. The second question is about breakthrough curves. The breakthrough curve, in my view, and it was also explained by Nick Wilkins and Farouk on the other day, is that it is a characterization tool. It gives you an indication of how the fronts propagate and how the interaction between the heat and mass transfer is. It does not tell you anything about the process. You can run one breakthrough experiment, and as I showed you earlier, you could now come up with a whole whack of processes, and each of them will give you very different results. So I would caution you from using breakthrough curves as they are in being able to make any broad estimates of how well the process could do. So take it for what it is, use it as a characterization tool, and then you have to look at some level of process modeling.
Thanks again, Arvind. So you can continue with the second part, and we'll ask you the remaining questions after the end of it.
Sorry, I think I'm already an hour into it, so let me try to get this quickly. Okay. So we are moving on to the second, also I would be available after this talk to answer all the questions. So so thank you for the patience. So the second part of my talk is about, let me just close this. Yeah, the second part of the talk is about adsorbent screening. So if you look at one of the grand challenges in adsorption research, if I may just use this, is to go all the way from pores to the planet. So what we are trying to achieve here is the expectation that if you know something about the pores, by either doing experiments or by doing molecular simulations, we can predict its properties such as isotherms. And once we know the isotherms, the engineers can step in and they can develop processes. And once we know the process and the performance of the process, we could now use system studies to estimate costs and life cycle assessments on the processes and scale it up to the plant scale. And once we know what happens in the plant, we can now have an indication of how it is going to affect the planet, and in this case with CO2 emissions, for example. So the holy grail, if I may call it, is really to say, can I go from all the way from pores to planets in a completely computational way and also in a reliable way? Okay. And as you can see here, you are going from pores that are in the angstrom scale to planetary scale. So you're probably trillion or more times a scale up is being expected. And this is a huge jump if you think of what chemical engineers traditionally deal with. Okay. So in this particular talk, I'm going to just focus on a smaller area in which this talk is centered around, is to talk about the pores to process. If you now zoom in to what happens here, this is a typical framework that happens to go from pores to process. So what you typically do is you either synthesize an adsorbent in the lab or on your computer. If you do it, you're usually doing it in the milligram scale. And then you start characterizing. At this point, you are measuring properties such as porosity, surface area, and all the properties, for example, that were discussed by Matthias Thomas in his webinar. So once you do this, the next level is to start calculating, for example, the first obvious aspect is the selectivity. How much does my stronger gas adsorb more than the lighter gas? And then, as I showed you, you also calculate the working capacity, and you also start calculating figures of merit. This is the point at which you start screening. And when you start with many adsorbents, this screening leads to a fewer set of adsorbents that can be now scaled up. And you're at least trying to produce tens of grams of material. Not many academic labs have this capability. And this is also a significant, I would say, input in terms of time and money. And this is the point at which you start measuring properties such as binary isotherms, mass transfers, which is critical. Stefano Brandani spoke about this, and Enzo and Stefano. And also you start doing column dynamics. So you start packing them into columns and start measuring what are called as breakthrough curves. And with this information, you put this into a computer simulation, into a process design and optimization. This is the point at which you are now starting to build the processes that I showed you earlier. And by simulations, you're also trying to guide the experimentation. At this level, as you can see, the properties that you're interested are purities, recoveries, energy, and productivity. And of course, you also have to make these processes continuous. So you're also worrying about how to schedule these processes. And ultimately, you're going to try and cost. As you can see here, this domain here is predominantly within the axis of the chemists. And this is where the engineers step in. So the adsorbent screening seems to be a point at which the chemist really hands over the baton to the engineers in order to continue. So, and that is why this adsorbent screening becomes so crucial in this entire framework. So if I now look at the grand challenge, just the three steps that, or the two steps that I wanted to focus, in order to go from pores to properties, as I call it, you can either do experiments or you can do a molecular modeling, which is increasingly becoming the method. Randy Snur gave a fantastic webinar on this. And once you have the property, we can start building processes either by, if you have the material, either by experiments or by process models. So while I don't want to, let's say, offend any of our colleagues in chemistry, an engineer, for example, sees an adsorbent in this form. For an engineer, the adsorbent is the isotherm, and that is where we start with, right? So that is really one of the key pieces of information that allows the two areas to communicate with each other. So now what has happened in the recent years is the following. So in the materials toolbox, this is a nice paper from Payman a few years ago that shows the increase in terms of the number of MOFs and other materials that are being generated. Yesterday, we heard from Stefan Kaskel that about 20,000 porous MOFs are available, but these continue to grow at an exponential rate. And there are also several databases that curate many of these. The NIST has a nice experimental database. The core MOF, which is developed by Greg Chung and co-workers, is called the Computationally Ready Experimental Metal Organic Framework. So they give information that molecular modeling community can use to predict properties. And there are also other databases. On the process side, you have process toolbox. As a process engineer, I have these toolboxes that I can play with. I can play with my operational. So you could either choose a PSA, VSA, a combination of these. You can also run it as a fixed bed, a moving bed, rotating beds. For example, the process that Svante uses is a rotating bed. And you can choose any of these. And within these operational schemes, you have configurational. If I take a PSA or a VSA, as I showed you earlier, you can now build different kinds of processes. So now you need to now map these hundreds of thousands of possibilities in the materials toolbox to that in the process toolbox. And this, as you can imagine, is a huge task. And the more important point being that you need to do this reliably, right? So if you now look at how this is done in most of the cases is, instead of using engineering, we often end up using process metrics. Process metrics are nothing but simple expressions that allow you to estimate qualitatively, in my view, how good is the adsorbent in being able to separate a mixture. Right? So it could be selectivity. I've spoken about working capacity. It could be combinations of all of this. And this is what is being currently used for many, many studies, especially in the molecular simulation domain, where there is a huge amount of data that can be generated using computers. In order to decide which material should be moved up the framework, people use process metrics. And a few years ago with Ashwin and Adolfo, we asked the question, do these screening metrics actually predict the process performance? And we took a toy example here. So here I show the isotherms for CO2 on 4 different materials. This is the famous magnesium of 74. The blue is the zeolite 13X. Red is another metal organic framework called as UTSA. And this one, the black is then activated carbon. So if you look at the CO2 isotherms, and if I ask you to pick the material that you think is going to win, in many cases, even before we did this study, I would have picked a magnesium off, because look at it at around 0.15 bar pressure, it has a huge capacity. And even if I now lower the pressure to about 0.01, 0.02 bars, I get a huge working capacity in this case. Or should I choose activated carbon? So it becomes very subjective, right? So you would usually move towards picking a material that you think is the best suited for this. So let me add a little bit more information. So here you see that in this case, I've now added, in addition to the CO2 isotherms, I've also added the nitrogen isotherms. And what you see here is that the magnesium off, shown here in green, while it absorbs a lot of CO2, also takes up a lot of nitrogen. Whereas the UTSA, which is shown in red, and note that I'm just showing these in log scale so that I can show both CO2 and nitrogen at the same time. You see that here, you're looking at the UTSA, it has a very poor nitrogen potential. So now the question is, which one will you choose? Okay. Let me throw in a few more. So now you can now go ahead and calculate all the different screening metrics that have been proposed in the literature. I'll not go into the details. It is available in the paper that I just showed you. But the main argument being, if you now rank them, these 4 materials, going from the best shown here in green to the worst shown here in red, you start seeing data that is everywhere. For example, if you see that a few metrics suggest that you should be picking magnesium off, a few others say you should pick up 13X, and a few others say you should pick up the UTSA. But all of them consistently say that do not pick the activated carbon. Now, with this additional information, which one should you choose in order to move on? So the best test, as I showed you, is to now run it through a process. And what we're going to do here is, in this approach, we are giving all the materials the same process, giving them the same ranges. And we are saying, now let us pick the operating conditions that best exploits the property of each material. So you're not choosing an operating condition that suits one material over the other, but you're giving them equal opportunity. And then you're now trying to span the entire operating range in order to find which material you should choose. And again, we represent them in the form of a Pareto curve. As you can see here, this is a purity recovery Pareto curve. Going from bottom left to top right makes it better. As you can see here, consistently, activated carbon performs poorly. And if you look at the performance of the other 3, although they show so much of a difference in their isotherm, you see that the difference is not very much. In fact, if you want to nitpick, a magnesium off performs poorer compared to UTSA 16. UTSA 16 among these materials has the lowest CO2 capacity, right? So that is very surprising, because that is a counterintuitive result that you would have never expected, just either by looking at the isotherms here or by looking at your performance metrics. The more important measure would, of course, be to look at productivity and energy for a constrained purity. In this case, I believe it was 90% recovery and purity. So which means if you go to the bottom right, higher productivity and lower energy, you have a better material. So this clearly shows that magnesium off, although it has very similar purity recovery performance, performs very poorly in terms of the energy and productivity, whereas the UTSA 16 does a far better job. So this is the real power of using these optimization tools. You give each material its entire scope to be optimized, and then you compare the optimum results. You're not choosing the best from one and the worst from the other. So this again shows that simple metrics don't work well. And as Amir pointed out in his question, the key factor that decided why UTSA was better compared to magnesium morph in this particular case was that it exhibited weaker nitrogen adsorption. So this was a very important point. Paul Webley had noted this in one of his papers. It almost seems like, at least for these kind of cycles, for vacuum swing adsorption cycles, the entire process seems to be driven not by CO2, but by nitrogen. This goes to the point one of our colleagues asked during the Q&A session. Can I now make a decision based on just one material? So if you had only measured CO2 and not measured nitrogen, you would never notice this. And this again tells us why you need to measure the isotherms of both gases if you're trying to separate two, and if possible, also get competitive data. Have there been other confirmations? Yeah, there have been plenty of other confirmations in the literature. I would particularly point out these papers from the groups of Randy Snur, from Farouk, from Stefano Brandani and Lev Sarkisov, and also there's a nice recent paper from colleagues in Georgia Tech, where this keeps repeating itself, where all of them say that simple metrics should not be trusted, especially if you want to make big decisions. Okay. Now, the obvious question is, why don't they work? And these are just my views on this. In my view, I think metrics were developed for qualitative comparison of isotherms, not really for screening. So if you look at it, earlier than about 10 years, we did not have this problem. It's a nice problem to have, of having opportunities through these tens of thousands of materials. So the screening of databases did not exist earlier. So we were really using it to judge why one material is performing better than the other, more so in a qualitative way and not a quantitative way. And the second point is that the metrics don't account for process complexity. And I think I've shown you this a while ago. In the simulation, as you saw in a column, the state variables, pressure, temperature, composition, keep varying in both space and time. So it begs the question, how do you now estimate a metric? What is a metric? At what point are you measuring it? At what time are you measuring it? So also, the metrics, as I showed you before, if you remember the 4-step and the 4-step LPP cycles, just by changing one small step, the whole process performance changed. So the metrics don't account for such complexities and the complexities of the cycle design. Metrics do not account for constraints. So now if I now have to say, enforce these constraints and then ask which material will perform better, the metrics don't give you that opportunity to do that. And in my view, this is very, very critical. If you're assessing the performance of materials, you have to put them on the same frame. If you're allowing one material to have a recovery of 40%, but a lower energy, and you're trying to compare it with another material that gives you 90% recovery, but at a higher energy, you're not comparing apples to apples. Right? So that is a very critical aspect that's often missed when you're using metrics. So obvious question is, should I completely abandon the metrics? My suggestion is no, do not abandon them. Why? Because they're very useful for understanding the broad trends that you see. Right? And even when process engineers are talking about understanding how these fronts move, we often talk in terms of these metrics. But my caution is that do not use them in a quantitative manner. And as I showed you earlier with the activated carbon case, they are usually good at identifying the really bad ones. Knowing good from great is challenging using these metrics. So now that I've shown that metrics are not very reliable, what other options can we offer? So, and for that, I show you here, what are the other process modeling tools that are available. So here I've plotted on the x-axis a qualitative time of how much computational time it requires. And on the y-axis, I've also shown how reliable are these in predicting the optimum performance. We can, of course, discuss about where exactly these blocks should be, but I think they give a big picture. And I've shown you here the computational time for one adsorbent on one core. So if you look at process metrics, they're fast, but very low reliability. You can now do process simulations like the ones that I showed. It usually takes a few minutes. You increase your reliability. And then once you have the simulations, you can now do a couple of parametric studies. You can change the velocity, you can change the pressure, you get some idea. That takes a lot more time, but increases your reliability. And then you can also do simplified models. And depending on how you develop these simplified models, they can be very fast and also be very reliable. Optimization, the method that I showed you earlier, requires much longer times. and it increases your reliability. Of course, on the top here is what are called as superstructures. What I showed you earlier was a limited set of PSA configurations. And now you can have a computer develop those configurations by themselves. There are nice examples, I would say examples, maybe a couple from the group of Larry Beigler, but this is an area which is very computationally heavy, and probably that is where the future is going to be. But this is where our target is. This is what we want to achieve. So we want to do it fast with high reliability. In this presentation, I'm going to talk about these two approaches, simplified models and full models. One of the first papers that, in my view, that started talking about simplified models, there have been plenty of papers earlier also talking about equilibrium theory design. But Paul Webley and Brian Maring came up with this nice paper that developed a simplified batch adsorber kind of a model to screen. And based on this paper, there have been many other papers that have come out, both from our group here and also from Lisa Yoss's group, formerly at Manchester, together with Megan Jobson. And also there was a recent paper earlier this year from the group of Camille Petit. So these are all, I would say, children that appeared from this model. So I would like to focus on what we developed, and the code that is used for this model is available for free. You can download this from GitHub. And what we require in these models are the inputs, the solid density, and the CO2 and nitrogen isotherm. If you know the binary isotherms, you can also use that. And then we've put this into what is called as a batch adsorber analog model. We framed it calling BAM. It's had a good sound to it. And what it gives you is it gives you a graphical design, and it tells you whether your process can meet the US Department of Energy criteria, 95% purity and 90% recovery. And it gives you the energy. It does not give you the productivity because of a critical assumption that we make. So without going too much into the details, I'll illustrate how this works. On the left-hand side here, I'm going to show you a cell. And the assumptions are that it is isothermal, it is equilibrium, which means that the solid and the fluid are always at equilibrium, which means you can use the isotherm to understand how this model works. And you're also working with a well-mixed system. What I want to emulate here is the process that I show here, which is the fourth step with a light product pressurization. So we start with and on the right-hand side here, I show you the isotherm. This is for 13x for CO2. These colored lines here are the CO2 loadings for different composition. For example, if I fix my CO2 composition to 15% at typical for post-combustion, this is how the loading is. And on the x-axis, I give you the total pressure. So we start with a system that has 1 bar and 15% CO2, which is essentially the feed. And then we desorb this. And when we desorb this, you start increasing the concentration of CO2 because it predominantly releases nitrogen, and you travel along this. Note that this is not a straight line, but it is obtained by solving two differential equations. And you can trace this path here. And as you can see, you've moved from a 15% line to 100% CO2 in this case. So the next step is evacuation. I try to lower the pressure again. So I go from B, and I now go to state gamma, which is lowering the pressure. I require this because I have to remove CO2 as my product. So this is really where I get the product. Then I pressurize it. So that takes me back to 1 bar pressure and a different CO2 composition. Since we are pressurizing with nitrogen, note that the CO2 composition in the bed goes from 100% to only about 3%. And finally, you perform the adsorption step that takes you back. So this is the cycle, and the advantage is here is that you're really working with a cycle where you don't have to keep repeating this over and over again because you end up with a cyclic steady state. The advantage, of course, is that this is fast. You can get results in less than a second. But I have to caution that this is a simplified model. So what we did was we took this and we ran detailed simulations and we calibrated the model. So all that we said was, if this model gives me a purity and recovery value of this, a true process would give me a scaled value of purity, recovery, and energy. So that calibration is very, very critical. If you don't have that calibration, you might not be comparing materials on the same platform. So now, what did we do with that? We screened a massive database, which is the carbon capture material database, originally created by Baron Schmidt and Lin Qianglin. It is available online, and I should also thank Bojit Baun and Adam Berger for sharing the data with us. And what we do here is we start with hypothetical zeolites, zeolite emitters-late frameworks, and what are called as IZA zeolites. From the carbon capture material database, we start with about 120,000. And we use the calibrated surrogate model, the one that I just mentioned, BAM in this case, to narrow this down to a few materials. So once we narrow this down, we then use a detailed process model to assess whether whatever we got from the BAM was actually good. So this allows us to go from about 120,000 materials, first screen them using a simplified model, and then use a detailed model so that we are only picking the materials that seem promising. So here are the results. So I've classified them as hypothetical zeolites, IZA zeolites, and ZIFs. In this plot, I'm plotting the Henry constant of nitrogen on the X and the Henry constant of CO2 on the Y. The green dots, so each dot here represents one material which is optimized for its performance using the BAM. So it's a simplified model. And the red ones are the ones that fail the DOE targets, and the green ones are the ones that meet the DOE targets. And what you see is that in all of these cases, you have, and these diagonal lines represent constant selectivity. So this shows that you require at least 10, a minimum selectivity of a Henry selectivity of 10 in order to be able to pass the DOE test. Again, let me caution, this 10 is not a sufficient condition. It is a necessary condition for it to even work for this process, for the given operating conditions, and for the given feed composition. So please be cautious in extrapolating these to other situations. So in other words, if your material has a selectivity of less than 10, you can safely keep it away and then move on. So what I show here is also the energy consumption for each of these points, the optimized energy consumption. The black dots are the ones that show an energy consumption of less than about 145, which is for the benchmark, which is 13x. And what you see here again is that when you have selectivity, so these are low selectivities, and you increase the selectivity by moving towards the left. At low selectivities, the energies, yellow means very high energy. You don't want that. You want to be in the blue region. So, and that happens predominantly at fairly high selectivities. And there is also a nice band in which the materials that actually produce energies less than 145 remain. Okay. I'll show you more of this in a couple of slides. What we also observed is when we plotted the energies on the delta H nitrogen, the heat of adsorption for nitrogen and CO2, we also found that there was a specific band over which most of the low energy materials were positioned. And this was in the region of, I believe, about 32 to 42 kilojoules per mole. So that seems to be a region where a lot of promising materials seem to be. If you go beyond that, you clearly see that the energy that you require to perform the separation is much higher. So we plotted, for example, the energy against the selectivity. Of course, 0 to 10 does not show up at all because it does not meet our requirements. And what you see here is something very interesting. So here we increase the selectivity as we go from the left to the right. And if you look at the average, which is given by the red horizontal lines, because that is what the box plot represents, you see that on an average, it goes down until about 500 to 1,000, and then it starts to come up. So this clearly reveals the fact that selectivity, just because a material has a higher selectivity, does not guarantee that it gives you a better performance. And there seems to be an optimum selectivity. So it is not that our aim should not be in trying to get a material that has a huge selectivity. And if you're aiming for that, my suggestion is aim in such a way that your nitrogen is lower, not by having a higher CO2 affinity. Okay, so that is a very key principle. The other point that you also note is that there is a fair amount of spread in these materials. So if you take, for example, a material which has a higher selectivity way here, so you could end up with an energy that is about 170, I'm, for example, pointing to this, whereas another material with a selectivity of only about 50 can give you a much better energy consumption. So looking at just the selectivity alone is not the right way to do this. Okay? So this is a very, very important observation in my in our study. And I would also like to point out the spread that you see in these. So which means if you're now trying to use these trends as a way to guide your selection, you have to be cognizant that you're looking at an average and you're trying to adapt that to a specific material, and that should be avoided at all costs. So here is a summary of how the detailed optimization compared. As you can see here, zeolite 13X is about 145 kilowatt hour per ton. And there were materials, for example, blue is the hypothetical zeolites, the IZA zeolites are here, ZIFs are here, and these are what are called as synthesizable zeolites from this recent paper where they looked at the same database and they identified by using different criteria which of these zeolites have a higher likelihood of being synthesized. And you can see here there are some materials that give you energies that are lower than zeolite. And this is about 16 to 17%. Now, the real question that we need to ask is zeolite 13X is available in the market right now. And it is cheap. You could get it for $1 a kilogram, for example, right? So, and now the question is, how much effort does it require to take any of these materials and synthesize them from scratch and then compete with zeolites? Again, I'd like to point out that I'm only showing you results from energy because this model cannot give you productivity, and that is another aspect. But the main message is that you can use these models to make more reliable predictions compared to simplified metrics. So the next, I would like to go to screening with detailed models. And what I show here are examples of studies that have looked at fairly large databases. If you look at a couple of materials, there are plenty of papers. So here my criteria has been that what are the papers that has looked at process-based screening for a database that is bigger than, let's say, about 70 to 80 materials. There are these series of papers from the group of Farouk, and I would ask you to read them. Very, very interesting papers. Earlier last year, there was a nice paper also from Randy Snur's group, and earlier this year we had a paper working together with Tom Wu's group, where we screened thousands of metal organic frameworks. So the idea is this. So you start with the crystal information from a database such as the CoreMorph database, and you use grand canonical Monte Carlo simulations, the ones that Randy Snur spoke about, predict CO2, nitrogen isotherms, and if possible, also competitive. And this is a place where I think a lot more work needs to be done. And once you get your isotherms, you start putting them into a process. Here we fix the process, but we optimize the process for all of these materials. So I can summarize it here. So we started with about 5,000 MOFs. We removed MOFs that were either toxic or contained rare earth. From our previous understanding, we knew that CO2 nitrogen selectivity should be greater than 10. So anything that was less than 10 was eliminated. That brought us to about 1,500 MOFs. And for these, we performed simulations, first using a coarser grid and then with a more finer optimization. So this represented over 5.5 million unique combinations of material and process configurations. So this was computationally heavy, but I believe we could do that with the help of Compute Canada, in a fantastic organization here in Canada. So if you look at the scale, we are going from molecular structures all the way to process optimization. So here are the results. I would refer you to the paper for the details. So what we found here is selectivity against parasitic energy. Here is the thermodynamic separation limit, and this is what we calculated as a liquid amine scrubber energies to be, including compression. And in this case, I believe we used a vacuum pump efficiency of about 60%, and I'll come back to that later on. And what we see here is, one, that as a function of selectivity, you don't see any particular trend in energy. Again, emphasizing the same point again. And you can also find materials that perform better than zeolite 13X. For example, we found UTSA 16. Another MOF that comes up is called as an ISERP MOF, and this is turning out to be fairly promising as well. We also show the working capacity against productivity. There is a gentle trend in this direction, but also there is too much scatter. And as you can see here, again, there are materials that can do better than zeolite 13X in terms of both productivity as well. In the paper, we also provide another plot which shows the trade-off that you can get between parasitic energy and productivity. So when we looked at the isotherms, so these light lines show the isotherms of each material that we screened. And we looked at what are the materials that failed the DOE isotherm, and we constructed an average isotherm of all the materials that failed the DOE targets and all the materials that passed the DOE targets, so that is given by the blue. And we just chose the ones that had the top 150 materials that show the least energy, and we constructed the average isotherm for this. And when you overlay these average isotherms along with your standard deviations, you see something very interesting. Of course, the DOE and the top 150 seem to be very similar, but also there isn't much of a difference between the average CO2 and isotherms of the ones that failed and the ones that passed. There is, of course, you have a higher capacity for the materials that passed, but if you now include the standard deviations, you don't see too much of a difference. So it is difficult to estimate performance simply from the CO2 isotherm. That again goes back to the question that we received during the break. If you look at the nitrogen isotherms, you again see that things that failed have a significantly higher nitrogen isotherm, and you require a lower nitrogen isotherm in order to have a better separation. This again emphasizes the fact that this separation seems to be driven a lot more by nitrogen than by CO2. Then the obvious question is, which is the best material? And this is a nice study that the group of Farouk did. And what they did here was very interesting. So they said, now let us pick the decision variables. And in addition to the process variables that I shown you earlier, let us also include the isotherm characteristics. So now the question is, what is the best isotherm that is going to result in a certain objective? And what they did was, in different papers, they've looked at different objectives, and the results are shown here. For example, on the left-hand side, we show the CO2 isotherm as a reference in the gray, and the UTSA isotherm here in the orange dots. So they did 3 different optimization studies. One, if your objective is to minimize energy, how are the CO2 isotherms going to look like? And that gives you a CO2 isotherm, which is right here. And the corresponding nitrogen isotherm is given here. Then they asked, okay, I'm not worried about the energy. Tell me what material or which isotherm will maximize my productivity. And what you see here is a dramatic shift in the material that is going to now give you the best productivity. Of course, the next question is, what will give me the lowest cost? And here is the lowest cost isotherms that they predicted. And you see that this lowest cost isotherm is kind of course, intermediate between the productivity and energy, because you would expect that trade-off to work. But it is, again, different from any of these. This drives home a very, very important point, in my opinion. Because very often the question that we get is, what is the best material? And the answer, in my opinion, is the best depends on really what you want to achieve. So your material might not be good in terms of meeting energy. Maybe it is better in terms of meeting the cost. So, and these are aspects that are typically not captured by using very simple approaches to measure the potential of these materials. And they also looked at the cost. What is it that is contributing to the cost? One is they noticed that compared to the NETL baseline, which is for absorption, 13X is still higher. But on the other hand, materials like UTSA or the integrated processes or the integrated optimized materials can, of course, produce lower costs. And the big uncertainty in this was, of course, the cost of the material. They had assumed a fairly low cost of the adsorbent, but it helps you to understand what is the best that you can achieve in this case. And if you look at the breakdown, it is very illustrative. The costs were dominated by capital and also operating, but capital seems to be a very, very big player. And this is because in their calculations for a 500 megawatt coal plant, they required hundreds of trains, each train consisting of tens of different columns. So you are essentially thinking about a column farm to do this operation. So in other words, if you ignore capital in your calculations, or if you ignore productivity in your calculations, which is only a surrogate, it is not a direct indicator of the capital, you might tend to completely get your calculations off. So if you look at what are the contributions to the capital, you see that a lot of it is contributed because you need a large amount of pumps, you need a lot of columns, so they tend to dominate the costs. And when they also did a parametric study to see how sensitive is their assumptions, they found that the vacuum pump efficiency, which I believe in the case was 60%, was the most. So they changed the vacuum pump efficiency by 50% plus and minus, and they calculated what would be the impact on the levelized cost of electricity. And they saw that that was a very, very critical aspect. And the adsorbent cost in their case was not. So this again shows that the simplest way that I can explain this is the adsorbent is, of course, the engine, but you don't get a car just with the engine. It is everything else that surrounds the car that is that makes the car more expensive or even make it run. So that is another level that we have to be aware of. So the last cost screening that I would like to talk about is a paper that came from Randy Snur's group. And what they did was they did the detailed optimization together with the cost, and they were trying to get to a generalized evaluation metric in order to make it simple for people to use it in order to screen. So what they did is they did the entire optimization, and they found what were the most important contributors. And the surprising fact was that it was a working capacity of nitrogen, not that of CO2, was the key feature that explained most of the change in their costs. So they came up with this kind of a generalized evaluation metric, as shown here. And here is the purity plot that they show. And they showed that as the generalized evaluation metric value goes up, your purities get better, and also your capture costs come lower. So they plot here in terms of Zeolite 13X as a reference, and they show that you could get up to about 25% improvement in terms of the cost. But also note the heavy scatter that you see here when you're using the generalized evaluation metric. So again, use them as a first level of screening, but always go to something more detailed. So how do I summarize everything that we have learned from looking at process optimization? One is simple metrics really don't work. Secondly, process and the objectives matter. The best material changes with your requirements for purity recovery, cycle, and or objective. I've shown that using Farouk's data. Nitrogen affinity matters a lot in this separation. So the best material typically is not decided by CO2 affinity alone, but nitrogen plays a huge role. So please do measure that data. Single stage capture requires low vacuum. From all our studies, 0.05 bar to about 0.07 bar is probably what is the best that we can get in order to meet purity and recovery in one single stage. You can, of course, increase the vacuum level so that you can, if you want to do that, you have to go to 2 stages or go for more advanced concepts. So if you want to do a single stage capture starting from 15% CO2, achieving 95% purity and 90% recovery, irrespective of the energy, requires very, very low vacuum pressures. And this has a huge consequence. As I showed you, energy, productivity, and complexity matter. These are huge operations, and we have to think about how to reduce the complexity. So this brings me to the last few slides. What are the real challenges when we go back to the ports to planet approach that we just discussed? And I've listed just a few here. In terms of ports to property, measuring both CO2 and nitrogen isotherms and impurities in water, if you have them better, are critical. Multi-component information is very, very important. I'll show you an example later on. Adsorption kinetics, which is very important in terms of being able to measure the cost, is hard to find. And very often we make assumptions in making these calculations, and that can have a huge impact as well. So that is also a call to our colleagues in molecular simulations to help us get better information about diffusion properties as well. In terms of going from properties to process, I think we need more experimental validations of these optimization approaches. We have just 1 or 2 in the literature, and if we want people to take this any seriously, I think we need to accelerate our validation, and the community should look towards that. We also have to use realistic process conditions, and this is something that has been lacking in our community, I would say, including ourselves, because the complexity of these calculations require that we simplify a lot of our initial conditions, and this has a huge impact. If we need to move this from pods to at least to the process level, we need to develop tools. And I will talk to you about this, that has to be rapid. They have to be reliable. They have to be robust, and they have to be ready to use. We really have to be addressing our colleagues in the materials community, not engineers, in order to provide them with the tools to make these decisions. In order to go from process to plant, sorbent costs continue to be unknown. So we end up making calculations that have huge uncertainties built into them. And we also don't have too much standardized costing tools because they don't have a plant of this scale built yet. So we have a long way to go in order to understand our assumptions on these costing. I'd like to just point out a couple of aspects here. So one is good data. And here I go back to the comments from Amir as well. So for instance, here I show the data from Nick Wilkins. So here what we did was we measured CO2 and nitrogen isotherms. The challenge in CO2 and nitrogen on 13X is simply that CO2 is very strong. Very often you use a dual site model to describe it, whereas nitrogen becomes a linear isotherm. So you really do not know how nitrogen would adsorb. So you start making educated guesses about how it does. And depending on how you combine the two sites in the isotherm, you can end up with very different performance indicators. So these are all the same operating conditions, same single component isotherm, different competitor description can lead to very different purities that are calculated in your simulations. This is another plot which Amir himself contributed in his paper. As you can see here, the way in which you fit your single component isotherms can also have a huge impact in terms of energy and productivity. So even in a case where you know how the single component isotherms behave, and to some extent also your competitive isotherm behaves, there is so much uncertainty in terms of your performance indicators. The second aspect that I would like to point out is also vacuum pump efficiencies. So the community typically uses a vacuum pump efficiency in the order of about 70% over the entire pressure range. And what we did in this paper was we looked at whatever vacuum pump information was available in the open literature, and we picked about 40 to 50 different pumps, and we plotted the efficiency as a function of pressure. Of course, the volumes and everything varies here, but you see a trend that at very high pressures, when I say high pressures, about 0.1 bar pressure, of course, the efficiencies are about 70 to 80%. But when the pressures go down, they drop dramatically. So very often in a VSA process, we end up working in this region and we end up assuming that you have a 70% efficiency. We want to understand what is the impact. So that is shown here. Here is an energy productivity Pareto plot. And the black line here shows what happens if you now fix your efficiency to 70%. And what if you let the efficiency vary according to this? And you see here, this Pareto for fixed efficiency now gets moved way up here. So which means you move from about 150 kilowatt hour per ton to over 350 kilowatt hour per ton. So your energy consumption can almost double if you take these vacuum pump efficiencies into account. So this is another crucial area where I think we need to start doing better in terms of predicting energy consumption from these processes. Pilot plant experiments also reveal very similar results as well. So in terms of tools, as I mentioned, you need rapid, reliable, ready-to-use tools. And I believe one of the ways that we can achieve this is by trying to make them go there using full models. And one of the areas which is emerging and which is quite fast is the use of machine learning. And together with the students here, we developed what we call as a MAPLE. We gave it a nice Canadian name and a Canadian logo. Which is machine-assisted adsorption process learning and emulation framework. What you do is you take an artificial neural network or any other statistical model, and you train this using a number of inputs, and then you use this for predicting the outputs. So there is a lot of effort that goes into the training, and you have to make a study of how much effort you need to put in. But once you have a trained model, then you can use that for performing these optimizations. So what I show here is the time it requires to optimize using a detailed model and the time that it requires to do the same optimization using a surrogate model. And you can reduce your time approximately by about 25 times. So this means now you can do things 25 times faster. and possibly get more reliable results moving on. So this is an area which looks very promising and that could change the way in which we are designing and developing adsorption processes. What I have not spoken about in this talk are issues about correct particle size, porosity. There's a nice paper from Brandani and Sarkisov that came out recently that talks about the importance of getting this right. I have not spoken about structures. Obviously, stability towards water and purity cycling are all important. When it comes to material, its availability and cost are critical. And in terms of processes, I've not spoken about complexity. These are huge challenges that we need to overcome. Vacuum pumps, the appropriate flow ranges and their efficiencies, and of course, costs. These are all critical in order to make any significant advance in CO2 capture. So that is my summary, and I will now be happy to take questions.
Thank you so much, Arvind. I think I speak for all when I say that this was a very clear and very interesting presentation. So thank you.
Thank you.
I'm going to start by the Q&A session. I'm going to start the Q&A session with questions from the previous part. So we still had 4 questions. Mm-hmm. Actually, some of them kind of seem to foresee this second part. Yep. So I'm going to start by the question from Stephen McDougall. Yep. Asking if these tools could be used to determine ideal process configurations. Is there anything you want to add on that?
Yeah, so what I showed you is when you look at the process configuration in this talk, we built them manually. And the advantage of running these detailed models is it also gives you an insight into how the fronts are moving. So looking at the fronts, you can decide what steps might be good or not good. So yes, so in principle, yes, but still I would say most of the configuration design is done manually. One of the aspects that could aid to that is the use of superstructures, which I briefly mentioned earlier. They are computationally challenging, but I believe that is where we will go eventually. But what this also gives you is when you now have 2 different configurations, it provides you the right way to compare and assess these configurations. And that is the key point here.
Great, thank you. Another question from the previous session was by Vincent NG, asking specifically which software tool you used for this optimization and which numerical methods. And he asked if in the calculations you also included valves in the simulation.
Okay. So in our case, we use MATLAB. So we use a finite volume scheme for solving. We use inbuilt MATLAB solvers. These are all described in our papers. And the optimization here is a genetic algorithm optimization. In our simulation, do we use valves? No, we don't use valves. But what we do is we use pressure curves that are measured from experiments, which include the dynamics of the valves in order to describe it in a more meaningful way. But of course, the right way and the more explicit way to do it would be, like as Vincent points out, would be to include valves and also, I would say, vacuum pump characteristics into your simulation.
Great. Maybe this maybe is connected. So a question from Sonalika Patel is, so how did you compensate the various losses, like the temperature and pressure losses during your optimization? And to what extent do you think the model can consider these various deviations?
So the first part would be temperatures. Most industrial scale columns would operate under adiabatic conditions. So we use that as a limit, but of course our models are not specific for adiabatic. You can allow for heat transfer. That is what happens in lab scale columns. So if you need to compare your calculations with experiments, you have to be cognizant of that. So we try to match, for example, when we do our breakthrough experiments to the temperature profiles as well. So that is how we get our heat performance. Pressure losses are calculated using an appropriate expression like the well-known Darcy's or Ergun's, depending on which operating regime you're working with. So these are, of course, taken into account.
Great, thank you. Our last question from the previous session is by Ravdeep Singh. And he's asking if the cycle times are always longer in the case of TSA compared to PSA and VSA, and if this lowers the throughput consequently.
From my understanding, yes, we have not, our group has not looked at TSA, but for example, you have looked at it in Zurich, and others have looked at it as well. Yeah, the thermal mass is an issue. So there has been a lot of proposals to run TSA in the form of a moving bed configuration. So in order to reduce the cycle times. So typically, yes, TSA tends to have a much longer cycle times, but I would ask you to also look at it in a much more broader context. It's not just the cycle time, but also how you can now use the energy. For example, TSA, you could potentially use waste heat that you may have in the plant, whereas in a VSA, you have to convert the heat to typically in electricity and then use it for your vacuum pumps. So when you're looking at it, I would say look at it in a more holistic manner. So again, pointing to the aspect that throughput might be low, but maybe there is an advantage that you get in energy.
Oh, thanks. So now passing on to the questions of the second half, we have another question from Małgorzata Kowalczyk, asking if the candidate material is not selective at the lab scale, can we simply skip all process optimization? And as an example, she presents a comparison of single component equilibrium isotherms.
As I showed you in this particular case, a minimum selectivity of at least 10 seems to be required. What we have also seen is if we now deal with a flue gas composition that is not 15%, that is about 12%, that selectivity range shifts. So what we see that as a necessary but an insufficient condition. So if in this case your material is showing anything less than 10, for a VSA application, again, I'll be very specific, for a VSA application under these conditions, you can safely skip and then move on. To reiterate the point, we also saw that the best energy, at least, seems to be at selectivities that are much higher than 10.
Great. Our next question is by Nirai Pandyan Sengyatevar, I hope I said that correctly, asking whether we use different adsorbent materials for PSA, VSA, and VPSA.
Yes, it's a good question. Whether do we use different materials, and a classic example is in terms of air separation. For example, there is a very nice review paper that came out in the Adsorption Journal written by Mark Ackley, where he shows how the characteristic of the adsorbent can be best suited for either PSA, VSA, or VPSA. He takes, if I remember right, the examples of lithium X, sodium X, and calcium X zeolites. And because of the shape of the isotherm, they lend either for a PSA, VSA, or a VPSA system. Yes, it has a very strong link to the process.
Great, thank you. Our next question is from Leanne, asking whether the screenings that you do are based on powder material. And if in this case, if you account for the effect of pelletization and binder in the screening models to achieve the DOE requirements.
Yeah, that's a good point. It seems to those assumptions also in the literature, I'm talking broadly, not just our group, but also other groups. In some cases, we assume that you can achieve, and again, I emphasize the fact, assume, that we achieve a density that is similar to that of zeolite, but without adding a binder in the form of a binderless particle. In some other approaches, we kind of delete about 20% of the capacity to account for a possible binder. So most of these calculations are done by assuming that you have a pelletized particle without a binder. And again, it has a huge impact, but on the other hand, think about it this way. This gives the best performance criteria for that material if it can be made into a solid with a binder, right?
Thank you. Another question from Małgorzata Kowalczyk is if you so the diffusion coefficients you use, are they computed from empirical relationships?
If you're going to make particles, and both Stefano and Farouk discussed this in their webinars, there has to be at least a macropore diffusion that will control. And at very low pressures, even Knudsen will start playing another key role. So in all our calculations, we at least take the macropore diffusion as a mechanism that governs the diffusion, and take the appropriate form of the macropore diffusion coefficient, and then calculate the linear driving force, the LDF coefficient from there. So which means there is also the impact of the molecular diffusion and the isotherm shape built into our mass transfer calculations.
Great, thank you. So now we're going to pass on two questions by Marco Mazzotti on your machine learning tool. Yep. He asks whether, so on your Maple tool, he asks whether you have shown that you can save the computation time by using the surrogate model with respect to full detailed models. But he asks what the impact of the training time is on this computation time.
A good point. And that is what is shown here. For example, if you look at this schematic here, the gray bar is for the time that you spend on sample set generation. So in the case of the surrogate model, almost all the time is spent on generating the sample set alone, in this case, right? Whereas in the case of detailed optimization, you spend a lot more time in running that over and over and over again. So in these cases, yes, you get a very quick payback in terms of the time that you'll spend on generating these samples, and we have seen that to be very favorable. And I think, did you have another question?
Yes, in fact,
yeah, can you use it for different adsorbents? I believe so. Yes. If you ask us in probably a month's time, I think I'll be able to give you a more definitive answer on that. And I think that is where the real holy grail is in terms of doing this.
Great, Arvind. Thank you so much. We don't have any more questions from YouTube nor from Zoom. So thank you again. And I think Dan will now take over.
Yep. Dan, I've turned off my...
Thank you, Arvind, for your presentation on large-scale screening of adsorbents. We'd also like to thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. Please join us on Monday, May 18th at our regular time, 10 a.m. New York, for a webinar on challenges in adsorbent development by Dr. Camille Petit of Imperial College London. Please also consider taking our survey at the URL noted on screen. We thank you for attending and hope that you have a wonderful day.
Oops.